And we are on to Chapter 3, Part 3. We're going to keep working on the math component of this. So before we move on to something new, I just wanted to quickly remind you that we had introduced a new unit factor in the last video. So again, we're back to doing math, just like Chapter 1. So our new unit factor introduced the mole, M-O-L-E, which is abbreviated M-O-L, and it is very much like a dozen in that it is a word that also can stand for a number in terms of counting. So 1 mole is equal to 6.022 times 10 to the 23rd of something. So I'm going to say things. So this works just like 1 dozen equals 12 things. Well, 1 mole equals 6.022 times 10 to the 23rd things. In the last video, we practiced doing some calculations starting with moles or solving for moles. Typically, the things that we're looking at in these problems are going to be atoms or molecules. They could be things like electrons. Oops, I'm getting real excited here. Electrons or protons or neutrons or very, very small things. I mentioned in the last video, mole doesn't have to just apply to atoms, molecules. It's just this number, 6.022 times 10 to the 23rd, is giant. So we don't have that number of larger items. So it's things that are microscopic, things that are smaller than our eyes can see, that we typically use this to group them. So that's awesome. But if atoms and molecules are smaller than our eyes can see, and I want to count them to figure out how many moles worth of atoms and molecules we have, I can't use my eyeballs to do that. Even using an electron microscope, I can see the outline of atoms, but that's not something you can easily count with. So there has to be another way for us to figure out how much is a mole of something. I mentioned in the last video that 1 mole, so 6.022 times 10 to the 23rd molecules of water, is about 1 big drink of water. So how do I know that? Well, it's our second unit factor, which is called molar mass. Molar mass is, by definition, the mass in 1 mole of a substance. Very clever. When I am looking at molar mass, I often abbreviate it, capital M, capital M. So if you see me abbreviate capital M, I'm talking about molar mass. And the units on molar mass is grams per 1 mole. So it's how many grams are in 1 mole of a substance. Okay. To figure that out, it's not always the same. It's not like with Avogadro's number, that's 6.022 times 10 to the 23rd. It's different for every substance. So what we're going to do is revisit that idea of formula weight or molecular weight, where if we had a molecule, we looked at the periodic table and we added up the masses of the average atomic mass of each element in that molecule until we got the total. And then we said that was how many atomic mass units, AMUs, were in 1 molecule. Well, it turns out those lovely numbers on the periodic table, the average atomic masses, they also work in grams compared to 1 mole. So the molar mass, we're going to determine for every substance that we're looking at by looking at the periodic table, and we're going to be using not the whole number that tells us the number of protons, but the decimal number. These numbers are what we're going to use. And so if I have KCl, well, I would take potassium's number, 39.0983, and add it to chlorine's number, which is over here, 35.4527, get my total, and that would be my molar mass in grams per mole. Now notice when I did my adding, I used the whole number. I didn't just say, oh, potassium is 39.0983, I'm going to call it 39. So remember that whole idea of significant figures and being accurate and precise? Why would we round stuff when we know more accurately what the values are? So in terms of molar mass, you're just going to add together the numbers from the periodic table, and we're going to go with the final answer, and it's going to have however many significant figures it has. And officially, we should use the addition, subtraction, sig fig rules, but at this point, I'm not super worried about it. So this is the periodic table you're going to use. You're not going to call oxygen's mass 16. You're going to call it 15.9994. Okay, so here's how we write the official unit factor for molar mass. 1 mole equals the molar mass in grams. Now I know this isn't a number. That's because it changes for every chemical formula depending on what the number on the periodic table says. Okay, so that's just how I refer to that unit factor. We now have 2 unit factors with mole. 1 mole equals 6.022 times 10 to the 23rd things, and 1 mole equals the molar mass in grams. So in every situation, either you're going to have to calculate the molar mass by using the periodic table to plug in a number. So a number is going to go right here. So that way you can use this as a unit factor, or I could give you the number in the question. So let's do some examples here. All right, so this first one. First, we need to figure out what the molar mass of nickel 2 nitrate is, and then we're going to determine the number of moles in 12.6 grams of nickel 2 nitrate. Actually, I guess backtracking, this unit factor makes it a lot easier to find moles because there are these lovely appliances called analytical balances that all you have to do is place chemicals or anything on them and it'll tell us the mass. So that's how I actually figured out that about 18 grams of water is 1 mole is using the molar mass. Okay, backtracking. We're going to do the molar mass. So we need to calculate the molar mass. I'm going to write MM for nickel 2 nitrate. So what I'm going to do is just look at how many atoms of each there are in this molecule, and then we're going to refer back to our periodic table, and we're going to go from there. So I have 1 nickel, so I'm going to have to look up the mass of nickel, but I only need it once. Nitrogens, well, we have 2 nitrogens, because there's 2 times 1. So 2 times whatever nitrogen is. And it's going to be, how many oxygens do you think there are in there? 6. 6 times however many, the mass for oxygen. And so we're going to have to do this, we're going to have to do this. And whatever that total is going to be the molar mass. So this, and this I'm going to look up on the periodic table, which is going to lead me to this being 58.6934. And this is going to be 14.00674. And this is going to be 15.9994. And when I grabbed my calculator and add all these together, I get 182.70288. That was the number I got. So putting this as a unit factor, 1 mole of nickel 2 nitrate equals 182.70288 grams of nickel 2 nitrate. So I can go ahead and I can even, just to be very clear, 1 mole of nickel 2 nitrate is equal to 182.70288 grams of nickel 2 nitrate. So that's a unit factor. That compares moles of nickel 2 nitrate to grams of nickel 2 nitrate. So that takes care of the first part of the question. Determine the molar mass. Well, the molar mass is 182.70288 grams. That's how many grams go in 1 mole of nickel 2 nitrate. The second question, which I didn't really pay much attention to until now, was determine the number of moles in 12.6 grams of nickel 2 nitrate. So this is a dimensional analysis type problem. We're just doing some math. So what unit do you think we want our answer in? Well, it's going to be moles, and I'm going to be very specific, of nickel 2 nitrate. Oops. Okay, so I can zoom. Can I write? Oh, it really wants the hand thingy. Hey, that's supposed, pretend like that's a 2. Okay. So when we're doing our dimensional analysis, it's what are we solving for? Moles of nickel 2 nitrate. What are we starting with? Well, 12.6 grams of nickel 2 nitrate. So I need a unit factor. Well, luckily, we just spent some time making ourselves our unit factor. So when I set this up, when I take the relationship between moles and grams, I need to turn them into a unit factor, which is making a fraction out of them. I'm going to put grams on the bottom because I need grams to cancel from what I'm starting with to down here. So the number 182.70288 grams of nickel 2 nitrate goes on the bottom. And the number 1 goes with the moles of nickel 2 nitrate. And I can cancel out the unit grams. The unit that's left is moles of nickel 2 nitrate. The unit I'm solving for is moles of nickel 2 nitrate. So I'm going to grab my calculator. Let's look at sig figs. Before I do that, my starting number has 3 significant figures. My unit factor here has 1, 2, 3, 4, 5, 6, 7, 8 significant figures. So my answer should have 3 significant figures. So I grab my calculator. I'm going to type in 12.6 divided by 182.70288. And what I get, and then I want to round it to 3 significant figures, would be 0.001 0.0690. Now looking at that, let's double check we agree that it has 3 significant figures. The zeros at the beginning, where we don't start counting significant figures until we're looking at the number left to right. We don't start counting until we get to a number that's not 0. That's 0. Can't start there. That's 0. Can't start there. That's a 6. Hey, we can start there. So that's significant. The 6 is significant. The 9 is significant. And then the 0 at the end. Zeros at the end are significant if there is a visible decimal place. Well, there is. So 3 significant figures. Okay. Let's try some more. What is the mass in grams of 6.33 moles of sodium hydrogen carbonate or sodium bicarbonate? And this is what they're going to look like when I give you the molar mass. See how in parentheses after that it says NaHCO3 equals 84.00661 grams per mole. That's me having already added up 1 sodium, 1 hydrogen, 1 carbon, and 3 oxygens. So that's my shortened way of saying 1 mole of NaHCO3 equals 84.00661 grams of NaHCO3. We still have to do the problem, but I saved you a little bit of time. So when we look at this, well, what unit are we solving for? Well, it says, what is the mass in grams? So we're solving for grams of sodium bicarbonate, which is baking soda, by the way. And we're starting with 6.33 moles. Now, I know we were also given that 84.00661, but that's our unit factor, right? And unit factors go in the middle. So 6.33 moles of NaHCO3. When I set this up, I'm going to take my unit factor up here. And I need to decide what needs to go in the denominator. Well, the unit mole needs to go in the denominator, so it'll cancel. So I'm going to put 1 mole down here. Oh, sorry, I'm getting excited and I'm thinking about the last example. NaHCO3, cancel out moles, cancel out moles. I'm left with grams, which is what I'm solving for. So I grab my calculator. Significant figures. This has 3 sig figs. This one has 1, 2, 3, 4, 5, 6, 7. So my answer should have 3. It's going to have the smallest. I'm going to take 6.33 times 84.00661. I get 531.7618413. I round that down to 3 sig figs, and I get 532. Grab your calculators. Make sure you're feeling okay as we do these. Okay. So let's just keep doing some more problems. Now, in chapter 1, once we learned how to do problems with 1 step, we moved on to problems with 2 steps. Well, now that we have 2 unit factors for the mole, that means those 2 unit factors could come out to play in the same question. Maybe I have grams and I want to know how many molecules there are. Well, then it's going to take me using the molar mass unit factor and the Avogadro's number unit factor to do that. This lovely visual doesn't help me at all, but if it helps you guys, it's awesome. It's just showing that we can bridge between grams and formula units, which are the shortened way of saying atoms or molecules. Okay, so let's try one of these. How many nitric acid molecules are in 4.20 grams of HNO3, which is nitric acid? And I'm telling us the molar mass of nitric acid, I've already looked it up, is 63.01288 grams are in 1 mole of nitric acid. So, read the question, figure out what we're solving for. Well, we're solving for nitric acid molecules. So molecules. Now be careful with molecules. You're going to have the temptation to want to abbreviate it because it's a long word. Well, don't we have something that is MOLE already? Isn't that a mole, which is its own unit? So with molecules, don't abbreviate. So molecules of HNO3 is what we're solving for. What we're starting with is 4.20 grams. I'm starting a little higher, I'm afraid, about space. So 4.20 grams of HNO3. And this is what we know. We have the molar mass of HNO3. So 1 mole of HNO3 equals 63.01288 grams. The other unit factor that we know, just generically, 1 mole of anything is equal to 6.022 times 10 to the 23rd things. And those things, in this case, are going to be molecules. Okay, so 2 unit factors, but I've got to start so I can cancel stuff out. So the unit that I'm starting with is grams. So I'm going to have to use the molar mass unit factor first because it's the only one that has grams. I need to put 63.01288 grams of HNO3 on the bottom, 1 mole of HNO3 on the top. Cancel out the unit grams. If I were to stop right now, my answer would be in moles, which is awesome, just not what I want. So that's why I'm getting ready for a second step. What I'm going to need to do is convert moles into molecules. So using my second unit factor, I know I have to put the 1 mole on the bottom, so it will cancel with the mole that's left up there. And the way I'm going to write this, 6.022 times 10 to the 23rd molecules of HNO3. And I have the unit that I'm looking for, so I went ahead and put my equal sign there. I cancel this out. Let's look at sig figs and then grab our calculators. 4.20 has 3 sig figs. The molar mass has 1, 2, 3, 4, 5, 6, 7 significant figures. Avogadro's number has 4 significant figures. My answer should have 3 significant figures, so I grab my calculator. 4.20 divided by 63.01288 multiplied by 6.022 times 10 to the 23rd. When I do that, and I want to round it to 3 significant figures, what I end up with is 4.01 times 10 to the 22nd molecules of HNO3. When you're solving for things like molecules or atoms, your number better be pretty big. It's going to be like times 10 to the something. If you're solving for grams or if you're solving for moles, your number should not be this large. Just a heads up on in case, you do the math and you're questioning whether your number worked out correctly in your calculator, because there's lots of ways that plugging things into your calculator can go wrong. Okay. Hopefully we're feeling okay on this. Let's keep doing some more. For this one, I'm going to add another step. This is almost the same question as the last one, but now it says how many oxygen atoms are in 4.20 grams of HNO3. So this time we're solving for atoms of oxygen, and we're still starting with 4.20 grams of HNO3. So, unit factors, we still have our molar mass, which is right here. We have our Avogadro's number. I'm being lazy. I'm not rewriting that. But I am going to start with 63.01288 grams of HNO3 in 1 mole of HNO3. And that is me utilizing this given molar mass, just following the molar mass unit factor. That would get my answer in moles. Awesome. But I need atoms. No, I can't go directly to atoms, but I can go to molecules using Avogadro's number. 1 mole of HNO3s, that's a 3, is equal to 6.022 times 10 to the 23rd molecules of HNO3. Now, you might say, I don't care about molecules, I care about atoms of oxygen. You got to be careful. That unit factor of Avogadro's number, whatever the moles are, so our moles were of HNO3. That's what it compares them to, how many HNO3s there are. You can't jump from moles of HNO3 and all of a sudden you're talking about H's or N's or O's. It's like saying I've got 24 people and saying, well, that 24, so a dozen is 12, right? So 24 is 24. So it's like saying, well, I have 24 people. That means I have 24 teeth. You're getting too detailed here. So when we're doing the Avogadro's number, if we have 1 mole of HNO3, we have 6.022 times 10 to the 23rd of HNO3. Like if we have 12 people, we have 12 people. I can't then break it down into smaller details. What we're going to have to do is continue on with our calculation to compare molecules to atoms of oxygen. So if I said I had 24 people, how many teeth are there? Well, we could say, well, 2 dozen, 1 dozen is 12, so times 2, that'd be 24 people. And then you need to know how many teeth are in a person, which I guess isn't always consistent, so that's a bad example. But anyway, there's another step to this. So our last step here is going to compare, well, okay, let's compare 1 molecule of HNO3 to atoms of oxygen inside of HNO3. So look at HNO3. How many oxygens are in 1 molecule? So just look at this. Well, I see 3. So that's that last step. So now I'm going to grab my calculator. 4.20 divided by 63.01288 times 6.022 times 10 to the 23rd times 3 sig figs. There's 3. There's, what did I say that was? 1, 2, 3, 4, 5, 6, 7. This has 4. And when we're looking at this last unit factor, you might think, oh, that has 1. Well, isn't this exact? In 1 molecule of nitric acid, there's exactly 3 atoms. There's not about 3 atoms. There's exact. So that's an infinite number of sig figs. So what's smaller? 3, 7, 4, or infinity? Well, our answer should have 3 significant figures. And when I do this math, I get 1.20 times 10 to the 23rd atoms of oxygen. If this has you scratching your head, just let me know so we can do some more examples. Okay, this is one that I want you to read the question. I give you the molar mass, so I've already looked it up. I want you to try this one, and then I will come, so I want you to read this, pause the video, try it, and then unpause the video so you can watch me go through it to see how you do. And again, I know it's super tempting to not do this. On tests, this is what you're going to have to do, is actually do the calculation. If you're just like, oh, yo, I got it, I would do exactly what you did. That's awesome, until you don't have my video in front of you while you're taking the test, going through the question that you're working on. It's really in your best interest to practice. So hit pause, work on this. Okay, so hopefully you're done practicing. Let's give this one a shot. How much does 4.16 times 10 to the 22nd molecules of CCl4, which is carbon tetrachloride, for remembering chapter 2, weigh in grams? So we're trying to figure out grams of CCl4. Oops, we're zooming in. Yes, and we're starting with 4.16 times 10 to the 22nd molecules of CCl4. So far in this chapter, I know 2 unit factors, Avogadro's number and molar mass. We've also used that looking inside of a formula, like going from molecules to atoms. That is a unit factor, but it's more of something we learned in chapter 2. So anyway, Avogadro's number and molar mass. When I'm looking at this and I got to figure out what unit factor to use here, I'm going to have to use Avogadro's number, because isn't that the one that is molecules? So 6.022 times 10 to the 23rd molecules of CCl4 are in 1 mole of CCl4. So if I stopped right now, my answer would be in moles of carbon tetrachloride, which is a wonderful thing, but we're looking for grams, so I'm not done. So I'm going to have to use the molar mass unit factor, which the molar mass unit factor is going to tell me there are in 1 mole of CCl4, there are 153.8215 grams. When I set this up, the 1 mole needs to go on the bottom so it can cancel with the unit mole right there. And the 153.8215 grams of CCl4 goes on top. So my unit that I want is grams, and what use that I'm at is grams, so it's time to grab my calculator. Let's look at sig figs. 3 sig figs. This has 4 sig figs. This has 1, 2, 3, 4, 5, 6, 7 sig figs. So my answer should have 3 sig figs. Grab my calculator. 4.16 times 10 to the 22nd divided by 6.022 times 10 to the 23rd multiplied by 153.8215. But I need to round to 3 significant figures. And when I got my answer and then I did my rounding, I got 10.6 grams of carbon tetrachloride. Hopefully this went well. If at the end of this, you set yours up just like mine, but the final answer that you got was different than mine, especially if it was like times 10 to the 47th or something, 45th, whatever, then it's something going on with your calculator, so it's time to talk to me about your calculator. Okay. So these last ones, again, I want you to practice them. So I want you to take this question, I want you to hit pause on the video, give it a shot, and then come back and I'll go through it. So Allison, C6H10OS2, is responsible for the smell of garlic, which I love, but I know not everyone does. Its molar mass, that I've already calculated from 6 carbons, 10 hydrogens, 1 oxygen, and 2 sulfurs, is 162.275 grams, or in 1 mole. We want to know how many moles of this Allison stuff are there in 5.00 mg. Crap, M. What is that? Oh yeah, that's from the metric prefix table in chapter 1 that we're supposed to like memorize and stuff. Yeah. So we're going to have to use the metric prefix unit factors beyond chapter 1. Welcome to chemistry. So we want to know how many moles of allicin there are in 5.00 milligrams of this stuff. So we're solving for moles of C6H10OS2, and we're starting with 5.00 milligrams of C6H10OS2. Now, my first step needs to be to cancel out milligrams. Well, what I know about milligrams is that there are 1,000 of them in 1 gram. Awesome. Now I have grams. That lets me then be able to use my unit factor for molar mass, which is there are 162.275 grams of C6H10OS2 in 1 mole of C6H10OS2. Cancel out grams, cancel out grams. The unit I'm left with is moles. The unit I'm solving for is moles. So it's time to grab my calculator. Let's look at sig figs first. 5.00 has 3 sig figs. The metric prefixes, do you remember how many sig figs they have? An infinite number of sig figs because they are definitions. And then the molar mass has 6 significant figures. So which one's smaller? 3, infinity, or 6? Hopefully your answer was 3. So when I do this, I'm going to write this in scientific notation because it was a pretty small number. 3.08 times 10 to the negative 5th moles, which would be 0.0000308. Both of those are correct answers. Okay, one more example. Still dealing with the allicin stuff. We want to know how many sulfur atoms there are in 5.00 milligrams of allicin. So again, I want you to hit pause, try this. When you're finished, hit play, and we'll go through it together. So we're solving for atoms of sulfur. I'm going to move this down. I have a feeling I'm going to take the whole way across to do this calculation. I'm starting with 5.00 milligrams of C6H10OS2. So step number 1 needs to be to cancel out the unit you're starting with. Well, we're starting with milligrams. So 1,000 milligrams are in 1 gram. Okay, now we have grams. Well, in this chapter, the only unit factor I have with grams is molar mass. So 162.275 grams of C6H10OS2 are in 1 mole of C6H10OS2. Cancel out grams. So I have moles, which is awesome. But I'm not solving for moles. I'm solving for atoms of sulfur. So I need to convert moles into things. So 1 mole, not at all going in a straight line, of C6H10OS2. I'm just going to kind of better. We can use Avogadro's number, 6.022 times 10 to the 23rd. But then what do you think those are going to be? What are going to be the things here? Well, we're going from moles. 1 mole equals 6.022 times 10 to the 23rd things. Well, it's going to be 6.022 times 10 to the 23rd of C6H10OS2. And the word for that are molecules. C6H10OS2. Awesome. Now I have molecules of C6H10OS2, but I'm solving for atoms of sulfur, so I'm getting ready for another step because I know I have another step. I need to compare molecules of C6H10OS2 to how many sulfur atoms are inside of it. So I'm going to start with 1 molecule, C6H10OS2. How many sulfur atoms are in there? Well, we're looking at the chemical formula. S2. So 2 sulfur atoms. Sig figs. 3 sig figs. Infinity sig figs. 6 sig figs. Oh, my puppy has hiccups. 4 sig figs. And infinity sig figs. So which one's smaller? 3, infinity, 6, 4, or infinity? Well, 3. Man, space-wise, this is ugly. So I'm going to take 5.00 divided by 1,000, divided by 162.275, multiplied by 6.022 times 10 to the 23rd, times 2. And when I go to 3 sig figs on that, I get 6.16 times 10 to the negative fifth. Nope, that's wrong. That is not what I get. Hold on. My calculator and I are not friends right now. I get this. 3.71 times 10 to the 19th atoms of sulfur. So remember, atoms and molecules, we should have big numbers at the end of this, which is why I knew there was something wrong with mine, because it was a times 10 to the negative fifth, which doesn't make any sense when we're talking about atoms or molecules. Because. All right, well, hopefully this went well. We're going to continue doing this type of math. These two unit factors are not going away, but just let me know if you have questions.